Hello everybody, we're getting ready to do Pre-Calculus Math Lesson 3.1 Part 3. Here's my email for note-taking guides, quizzes, tests, and tutoring and other things. Email me here. 3.1 Part 3, we got 46 points here. Classwork, no note-taking here. Classwork guides, when you're doing the lecture, will help you. Email me for that. Okay, so slide 1, 3.1 part 3, formulas for compound interest. After T years, the balance A in an account with principal P and an annual interest rate R is given by the following formulas here. For n compoundings per year, A equals P times quantity 1 plus R over n to the nt power. For continuous compounding, A equals PE to the RT. This is the good one here. Okay, example 8. Finding the balance for compound interest. $9,000 is invested at an annual interest rate of 2.5% compounded annually. Find the balance in the account after 5 years. Algebraic solution. In this case, principal equals 9,000, rate equals 2.5% or 0.025, n equals 1 because we got a compounded annually here, and then t would equal 5. So what that would look like when we plug that into our formula here, this is our formula for compound interest. N, remember, is 1, t is 5. So when we plug that in from our previous formula, we have this here. 0.025 over 1 to the 1 times 5. And then inside here, we have 1 plus this amount here. And then we substitute in. And then we have this here, 9,000 times 1.025 to the 5th power. And then when we simplify, we get this number here. For 2.5% compounded one time annually, we have this number here. So this is after 5 years. So a graphical solution, what that would look like on a graph would be this here. So when the balance in the account after 5 years, x equals 5, y would equal 10,182.67. And you can put this into your graphing calculator and find that out. Okay, so let's go to our first guided practice here. For this subject matter, we got 2,500 for t years, compounded n times per year. So, and then we go into continuous here, which is a different thing, but for our compounded annually here, then same thing down here, r equals 6%, t equals 10, and then we go into a continuous interest rate here. So for the first one here, here is our dynamic here, 2,500 at 2%, 0.02% is what this would look like for 10 years. So, and then we have a number here, we compounded it continuously as well. So for 12 years, it will be this number here. And then for 365, if we compounded it continuously, you would get another 51 cents here for 12 years. So that would, over time, I guess that adds up. But the principal is so small. But anyway, you would get that here, 51 extra cents. So 51 cents, 51 cents. So do that down here as well, 6%, and then t equals 10 years. Come up with your number here. So again, here is our formula. We plug in here, and we get that number. Okay, example 9, finding compound interest, 12,000, interest rate 3%, find the balance after 4 years for each type of compounding. So quarterly, for quarterly compoundings, n equals 4. 4 years, after 4 years at 3%. The balance would be right here. This is our formula for compound interest. And then we plug in our values here. 4 times if it's compounded quarterly, 4 times for 4 years. So we have 0.03, that's our interest rate. And we have a principal here of $12,000. So what does that look like when we grind the numbers here? We 13,523.91 cents using a calculator. And then for continuous compounding, let's see what that would be. So 12,000 e to the 0.034, substitute p, r, and t, and then we get 13,529. So we get $7 more. Using a calculator, we come up with this number here. For continuous compounding, the account yields more than a quarterly compounding. Yeah. So for continuous compounding, the balance would be that. So let's go into our guided practice here. We got continuous, and then we got this situation here. 4% for 20 years, 2,500 at a rate for 2 years, and compounded in times per year. Okay, so we have t equals 20 years. I guess it's 1 time a year. And then, well, yeah, and then down here we have 3% for 40 years. So let's see what the 20-year would look like here. Okay, compounded continuously, this is our formula here for 4% for 20 years. And this is what it would look like here. After 12 years, at 4%, 2,500, and you've more than doubled your money here. Continuously, it'd be 55, 63, 85. So you get a little bit more there. So it's advantageous to compound your principal continuously. Example 10, radioactive decay. So let Y represent a mass in grams of radioactive strontium, whose half-life is 29 years. The quantity of strontium present after T years is this formula here. Excuse me. What is the initial mass when T equals 0? So with this setup here, to find our initial mass, we have to make T equals 0. So when T equals 0, it'll be 10 to the 1/2 to the 0 power, which would just be 10. So the initial amount would be 10 grams at start. So when time equals 0, the start time, it would be 10 grams. So a graphical solution showing this function in the graph here, this is our function here. So your mass falls here, and then when x equals 0, y equals 10, that's your starting place, and then it falls like that. So after 80 years, so right, original equation, then we plug in 80 here. So using that function for 80 years, we get 10 to the 1/2 to the 2.759 power, which equals 1.48. So 1.48 grams are present after 80 years. So that's quite a fall there in mass. So a graphical solution again is this here, and then this shows it here when t equals 80, or when x equals 80, y equals 1.4776529. So you're right here. This is your amount after 80 years. That's your graphical solution. So now we go into our next guided practice. Independent practice. Let Q represent a mass in grams of carbon-14, whose half-life is 5,715 years. The quantity present after T years is given by 10 to the 1/2 T to the 5715. Determine the initial quantity when T equals 0. So that is our A. So, and then we have a C part of that as well. Determine the quantity. We have a graphing solution that we have to do as well. So when T equals 0, we start out with 10 grams. Okay, good. And then for B, when T equals 2,000, we have 7.85 grams. So we start at 10 grams of carbon-14, and then after 2,000 years, we have 7.85 grams after 2,000 years, using this formula here, using your calculator. And then for the graphing sketch, graph the function over the interval of T0 to T10,000. So to do that, let's see what the graph looks like. Here's your graph here. Starts at 10 grams, and then 10,000 years will be right here. So whatever that is, looks like a little bit less than 4 grams after 10,000 years. Okay, example 11, population growth. Fruit flies, Q of T equals 20e to the 0.03 T, where T is greater than or equal to 0. So find the initial number of fruit flies in the population. A, to find the initial population, evaluate Q of T when T equals 0. So to do that, we plug in 0 here for T equals 0. We have 20 flies. We start at 0 time. And then B here, how large is the population of fruit flies after 72 hours? So to do that, we have to plug that in. 20e to the 0.03 times 72. And when we crank that through, we get 173 flies. So after 72 hours, we got this amount of flies. So we're going to graph this now. So the graph of Q is here. Here's our function for the population growth of fruit flies, 20e to 0.03 T. Okay, our next guided practice. So population growth, California, 2015 through 2030. And then here's a function here, as supposedly models the California population growth. Use a graphing utility, graph the function. Use the table feature of the graphing utility to create a table of values for the same period as in part A. So, to do this, here's our table. So we have two tables here. What year would the population of California exceed 50 million? And we're going to use our table feature to find when California will exceed 50 million. So, to do this, first of all, we're going to graph this thing. Here's our graph here of using this function here for California's population growth. And then for a table from that function, here is our years here. We're at 2018 today. We got 41.3 million. I think actually California's got more than that actually now. And then when we finally hit 46.4 at 2030, what did it say, 50 million? So when will it hit 50 million? So we make this function equal to 50, and then when we crank it through, we find out 37.7 or 2037. So it will reach 50 million population at 2037. And that is our lesson for today in pre-calculus. Email me here for note-taking guides, tests, tutoring, etc. Thank you.